Hi, students, and welcome to the newest unit on probability. So in this unit, we're going to explore the concept of chance because it's directly related to statistics. And what understanding probability allows us to do is to extend what we know about a sample to a population by understanding how samples vary and what the probability is of selecting certain samples. So first off, we're going to have to talk about some basic vocabulary. In particular, we're going to talk about this concept of sample space. Sample space represents all the possible outcomes of a particular experiment. Now, a sample space consists of lots of simple events. So one particular outcome that has a probability of occurring. And when we combine multiple outcomes of these simple events, we can end up with a much more complex outcome or event. So let's extend this to rules of probability. So the rules of probability dictate that for the probability of any event, however complicated, it will always fall between 0 and 1, with 0 being impossible, 1 being a guarantee, and anything in between. Also important to note is the lower the percent or the lower the decimal, the closer to 0, the less likely the event is. Again, in inferential statistics, this will become very important to keep track of. And usually a cutoff is 5% or 0.05 to be considered unusual or unexpected. Since the probability of 1 guarantees a particular outcome, then if we take all the possible outcomes in the sample space and add up their probabilities, we will get 1. Because if the sample space consists of all possible simple events, then the summation of all those is a guarantee that something will happen. Moving into the next part, we're going to revisit this idea that we had prior that will help us understand probabilities even more. Another way to view a probability is as a relative frequency of an event. Now, if you recall, we calculated relative frequencies by taking the frequency of the event and dividing that by the total number of frequency. So what happens here is the same thing. We divide the frequency of the event, all the possible probabilities that are associated with that one, and we will divide it by the number of trials or experiments. So stating it yet another way, and these all mean the same thing. So the number of ways that an event can happen over the number of possible outcomes gives us probability. And while this all sounds great in theory, in the practical examples, it'll be much clearer in a moment. So let's look at a sample space of a very simple event. If you toss a single coin, you'll either land heads, which is a side with the face on it, or tails, which usually has some other symbol, but never a tail. So I don't know why it's called tails, but whatever is on the other side is considered tails. So if we look at an event such as flipping a head, what are the chances of that happening? You may have already figured it out. Since there's only one head, but there are 2 possibilities when you toss a coin, clearly the probability of this event is 1/2. Now let's consider the possibility of a head or tail. Now still, we're only doing the toss of one coin one time. So the probability of head or tail, what is that going to look like? Well, what's the chance of looking down and seeing either a head or a tail? You've probably guessed it. There are 2 possible outcomes related to the event over 2 possible outcomes in the entire sample space. So it's a guarantee. When you look down, you're going to see one or the other. Compare that to head and tail. If you look down at a coin, you're never going to see both sides of it at the same time. Therefore, there's no chance of that happening, which means it's impossible. Let's gradually increase the level of complexity and look at tossing a dice. So if you toss a single die, you'll notice that on the 6-sided cube, you'll see 1 dot, 2 dots, 3 dots, 4 dots, 5 dots, and 6 dots. So each side has its own numeric value associated with it. What's interesting is those dots, known as pips, are actually carved out of the play dice that you get in most of the games that you'll see. But in the casino, they actually filled the pips back in because that little bit of change by digging out that little piece of material actually changes the probability so that not all sides are equal unless you fill it back in. So if you ever go to the casino, there's no indentation. Just an interesting side fact. So what's the chance of rolling a 3? Well, there's only one event associated with that out of 6 events in the sample space. So therefore, it's a 1 out of 6 probability. Let's look at a number less than 4. So now there are lots of possibilities. You could roll anything less than a 4, which includes 3. It includes 2, and it includes 1. So that gives us 3 possibilities out of 6, which gives us a half. Now let's look into a number no greater than 2. Now, some of the ways of phrasing these events are tricky, but that's by design. To get used to understanding whatever the context is that's given to us. So a number no greater than 2 includes 2 and anything smaller. So in this case, 1 and 2 would satisfy a number no greater than 2. So we have 2 out of 6, which simplifies to 1/3. We're going to move on to even more complicated single event, which is selecting a card. The reason it's more complicated is because there can be overlapping events, and also there are just far more options here. There are actually 52 possibilities in the sample space because there are 52 individual cards that are all different in some way. So if we look at a deck of cards, what are some of the probability questions we could ask? Let's start with the possibility of selecting one suit. The suits are in each of the rows, and they consist of a club, a heart, a spade, and a diamond, if you read from top to bottom. I'm going through this because I know that some people actually haven't played card games before, so this setting might be unfamiliar. The other aspect of cards is that they run from ace through to 10, and then jack, queen, and king. So when we ask what is the probability of selecting a club, the question is asking what's the chance of selecting a card from the top row. And if you count them up, you'll have 13 cards out of 52 cards, which gives you 1/4. You could also see that's 1/4 because it's 1 out of the 4 rows. So of course, it'll simplify to that as well. Suppose we want to select a picture card. Now, when we say picture card, what we mean is something with a face. So we're looking at these 12 individuals over here. So what is the probability of selecting a picture card? It is 12 out of the 52, which simplifies to 3 out of 13. Now, the reason it simplifies to 3 out of 13 is if you look, there are 13 columns. And in this case, we're selecting 3 of those columns. Therefore, it also simplified to 3/13. Now, suppose we're combining events. What if we want to select a club and a picture card at the same time? Well, there are only 3 possibilities of that, the jack, queen, and king of clubs. So that gives us 3 out of 52. Now we're going to try selecting a card with or. Now recall we had or when we tossed a single coin. How does it work when we're talking about a deck of cards? So if we're selecting a single card, the chance of selecting a club or a picture card consists of selecting a club, which is that top row that we did before, which is 13 out of the 52, or 1/4. And it also consists of the picture cards, which we know are 12 out of 52, which simplified to 3/13. But using the 13 and the 12 are going to be easier. So let's combine the 13 and the 12, and that gives us 25 out of 52. But unfortunately, we're not finished. And the reason we haven't finished is because we've overcounted. In fact, we've overcounted by these 3 cards because they're both clubs and they are picture cards. So what we need to do is we need to remove them. And how do we do that? We subtract. When we subtract, we take away the fact that we counted them twice because we remove one of the times we overcounted. That brings us to a general rule. And this is the general addition rule, where if you have 2 probabilities combined with an or, you'll add the probability of each individually and subtract off the overlap because the overlap is contained within both of the separate probabilities. So you're always overcounting by the overlap, which in this case is the probability of E and F is the overlap. Now, suppose we want to not select something. In order to not select something, we leave it out. So if we plan to not select an ace, what would that look like? We could simply count up all the cards that are not an ace, or we could try approaching it a different way. We could try counting up the aces and then not including them. In this way, it would be a lot faster. Instead of trying to count 48 cards, we could simply take 4 away from 52, and that will give us 48 out of the 52 that are not aces. We also know by the columns that the 1 column is being removed from 13 columns, which leaves us with 12 out of 13 columns. So that brings us to another rule, the complement rule. So the complement rule simply states if you have an event that is stated as not a particular event that's easier to count, you can take away the probability of that event from 1 to get the event that you're looking for. And this is known as the complement rule, like we just did with the aces. So just to recap in this video, to try to make brief, we've only looked at single actions, a single coin toss, a single die roll, and selecting 1 card from a deck. In the next video, we're going to complicate matters by doing multiple things at once. I'll see you in that video soon.